Hi, everybody. Week two. Week two's almost over. Congrats to all of us. Let's settle in. Oh no, sorry. That's gonna be bad. I will forget that hat. Okay. Good job, we had. All right, just settling in and keep pulling away from your chair. Just letting your strength support your back. In a gentle way, you don't want to be straining. Try to find a spot of balance, and sometimes even just a little bit of teetering back and forth like a pendulum can find the perfect location. And just coming into contact with our body's experience. What are you feeling right now in terms of sensation? Let's focus on our hands for a little bit. Can you discern the shape of your hands purely based on the feeling of your hands? Where are the edges of your hands? Find yourself drifting into thought. Just take a notice of the thought. Try to back off and observe the thought. And come back to noticing the hands. Let's just gently come back together. Do some real analysis. I guess I should get out some real analysis. We can do it. So I've got an agenda, but I don't know. Do you have anything particular you'd like to talk about? We've got a homework, our first homework due on Friday. Yeah, there's a couple ways you could turn that in. Preferably, I'd like a hard copy just popped into my box outside my office. If you can't do that for some reason, a PDF scan, please. And let me know if I need to make a Dropbox, and I will do that, because I don't want my, please, two things to please not do. Don't send me JPEGs. Oh God, please don't send me JPEGs. They're horrible, because I will print out your assignment, and printing an image is always a really terrible thing. And then, yeah, please don't email it to me if possible. So just let me know and I'll hook you up and we'll both be happy. Does anyone have anything they want to talk about on that assignment? I think the second assignment, homework 2, is up. Is it? Is that true? Yeah, no, maybe?
I don't know.
Oh, okay, I thought you knew. Okay, I know I put it up. It might pop up today. Homework 2, if not, I will make sure that it does. I can give you that assignment if you want. Some people are probably done, have been done on the past assignment. So here, I'll just put that on the board for you. Very slow prep today. Okay, so homework 2 is going to be 1, 3, 1, 2. So it's problem 1 from section 1, 3, problem 2, 8, 9, and 11. I would say these are not trivial. It looks like a very small assignment. You don't need many problems in real analysis to have stuff to do. So some of these have multiple parts, and I would love on Monday to have people want to know things about these. Have done a little thought, dig in, let's talk about them on Monday. There's a lot to talk about. And then I would ask if you could also read 1-4 for Monday. Start reading through it. I guess I'm working on this assumption that everybody kind of knows how to read math. If you're like, I don't know what you mean when you say read this math or what the most efficient way to read math is, we can talk about that as a group, or I can talk about it individually, so just let me know. Michael, sir, yes?
I thought in that email you had wanted us to read 1-4.
For today. Yeah.
Oh, did I?
Yeah.
Woohoo! Good job. You don't have to do that then. That's great. Thank you. I don't know if we'll get there yet, but it's good to have that under your belt for sure. Thanks, Michael. So, anything to talk about? That problem with induction, that's going well. There's a problem that requires a bit, but yes, sir.
I understand how to start the first part of it because you always prove the case for one and then go from there. But
Right.
I do not understand how to start the second
There
part.
we go. There's a great question. Little bit of just like I had to jostle things just a little bit there. So let's take a look. That is problem.
1.2.12b.
Thank you, sir. Cool. So we've got this sequence that's being generated recursively. So this is 1, 2, 12. And we initialize the sequence with a 6, and then we generate subsequent terms with the following rule. So that, just when I get something like this, I just want to see what is it doing, right? The first thing you should always want is some concrete information in front of you. So let's just crank out a few of these terms. So y sub 2 is going to be 1/3 twice y sub 1 minus 6. So looks like a 2. Yeah. Just please, like it's like I haven't done math like in a couple of days here. So just keep me on task. Y3 is going to be 2 times 3 minus 6. That looks dead. But I don't think it's going to stay dead. And then y sub 4 is equal to zip minus 6. So negative 2. And it looks like we're going to stay negative then. So it's kind of this decreasing sequence. It seems to be, to me, that may not be the case. That might actually be what we're supposed to prove. Is that what we're supposed to prove? But it's let's see, what are we supposed to prove here?
I think I disagree with y3.
Oh.
Because y2 is 2, so then 2 times
Oh,
2.
yeah, good job, Kayla. Thanks for busting it. I mean, fixing it. busting my bullshit. So
That
let's
would
see
be
here.
Negative 2/3.
Negative 2/3, thank you, Anil. Yes. And then I need to redo this really quick. So then that's gonna be negative 4/3 minus 6, and,
Negative 28
thanks. Negative 28/9, is that what you said?
I think so.
That sounds good enough.
Yummy.
Does that sound right? Yeah,
Yeah.
yeah, okay, cool. Great, so the first thing we're asked to do here is prove that the sequence is always above -6. So there's something interesting happening here. There's two things happening. We're decreasing, and the first thing we're asked to prove is that the sequence never stops, has a lower bound. Not that it stops decreasing, but that it never decreases past a point. One good way to view sequences is to plot them. And I always like doing this too. I like visuals. I like that data that we have over there. So y sub 1, this is the k value here, is 6. So there's y sub 1, and then y sub 2 is a third of that. And then we actually go down to the negatives. So let's see, that's 3. So it gets really tiny, so negative 2/3 here. And then, wow, keeps on going. I'm not gonna plot that out, but I will say here's -6. So we're hopefully seeing some kind of asymptotic behavior there in that sequence. I mean, that must be what's happening for this thing to be true. So show that y sub k is never below 6 or even equal to 6 for all k. So at this point, this isn't too tricky because we've got a nice base case. So we know that this y sub 1 is greater than 6. So again, so for induction, you want a base. You have to anchor your inductive reasoning somewhere. And we have y sub 1 equals 6. That is clearly greater than -6. Then from this point, we're going to jump to our inductive case. So inductive step. Now, there should be pretty words around this. This is a skeleton. This is simply a skeleton of a proof. There could be, the things I'm saying I would write in words. So the inductive step is we're going to assume that y sub k is greater than -6. Using that information, show that implies y sub k plus 1 is greater than -6. If you look at the relationship between these two things, and the fact that this is a positive coefficient in front of the y sub k's, in fact, you might even want to do something like this. Multiply that out. You know that this is bounded above. Make an argument to show what is this quantity greater than if this is true. We know that this thing right here is greater than -6. There's actually like one more step, maybe two, tops on that. So I don't know that that's the question you had, Michael. It might be the next one. Okay, cool. So yeah, so now we want to show this sequence is decreasing. We intuited that, but we need to demonstrate it. So what I would do for the next one is decreasing, is first get a base case. So the base would be, we know that y sub 1 equals 6, and we cranked out y sub 2, and that was 2, and so clearly we're good to go on those first two. For the inductive step then, I'm going to assume that y sub k is greater than y sub k plus 1, And that might have been where you were like,
Yeah.
not quite sure what to assume there. And then use this to show that y sub k plus 1 is greater than y sub k plus 2. How would you do that? Well, you've got this assumption right here. And you've got a formula for both of these, right? So we know, let's just talk about some things that might help here. Helpful facts. Well, first off, the original relationship. I mean, that's what it has to come down to, because that's the only thing you know. But I do know something like this, that y sub k plus 2 is equal to 1/3 twice y sub k plus 1 minus 6. So already I've kind of got this guy who I don't understand back to something that I do understand. And I can do something similar here. This can be written in terms of y sub k. So just realize that each one of these can kind of be bootstrapped back to these two. And then you can use this fact to intuit that. Do your best. All I ask is that you try. Does that sound good, Michael? Awesome. Any other questions, or should I go through each question and say, what about this question? Yes, yay!
So I had asked you this last week, but are you, since I got used to it with linear, abstract algebra a lot, for 1.2.8, when we're talking about functions and based on the definitions they gave on functions, it's just a certain rule.
Mm-hmm.
This isn't one I use, but for example, I was thinking about it. If I did the natural numbers 1, 2, and I mapped both of them to 1, and then did 3, 4, and mapped both of them to 2, is that valid?
Oh,
To
totally.
use it? Okay.
In fact, let's talk about this question, because there's a great way to think about it, at least for my mind. Your mind varies, all our minds vary, but this idea of sketching out these sequences really can be helpful. So, let's see, what are we trying to do here? Let me take a look. Okay, we're asked to come up with examples or show that no such example exists, or at least argue that. You don't need a formal proof necessarily, but just an argument. So our function is this. It's got a domain in the naturals, and it's got a codomain in the naturals. So in other words, it spits out naturals, it takes in naturals. That means it's going to be a sequence. So this function is actually just a sequence, because I have f of 1 equals something, f of 2 equals something. And those are going to be whole numbers, or natural numbers. So that means they're going to take on integral values. So just to get a sense of what one of these functions looks like, I think Michael just said something like this. If this is 1, is this the function you just described, Michael? Something like that? Yeah. So drawing this picture out is super helpful, because I can look at this now. So let's see, then it goes up to 3 for a couple of terms, right? So a step function, but not always increasing. So I can look at this and say, oh, cool. I don't know, let's just make some observations about it. It's increasing. It's non-decreasing. Be a nice, clean way to say that. And it's not 1-to-1 either, right? So for a particular output, say 2, I've got 2 inputs achieving that output. So in other words, f of 3 is equal to f of 4. And then using this, I would say is a good way to work through this problem. So what would it mean to be onto? Onto would be, I actually have an output that achieves every single one of these natural numbers. So the way this is headed, this would definitely be onto, but not 1-to-1. And so this is the way that I'd like you to argue through this thing. Let's see, I don't want to give away the answers onto, well, I just gave away one, so don't use that. That's Michael's. Come up with a new one. It shouldn't be terribly difficult. One-to-one, but not onto. Think about how that could be. How could you make sure that you're not outputting two dots in the same level, but that, yeah, just that you're not outputting two dots on the same level. That's really all you have to be assured of there. And then one-to-one and onto, make sure that you don't do this and you hit all these outputs. You can probably even visualize it right now. So that I think is the way to think about this. You don't have to write out a formula either unless you want to feel challenged. So like for Michael's, this could be challenging to write out. You could do something like this. You could say, for Michael's, let's see, f of k is equal to, seems like if I divide by 2 and then round up, I'm probably good to go. So if I take k over 2, and make sure that that's never a fractional thing. So let's see, so when k is 1, that would be 1/2. I want to round up. So I use this thing called the ceiling function. If I can spell ceiling. Oh, how embarrassing. Is it I-E?
I don't know.
I think it might be EI because it's I before E except after C.
Oh, you are a master of things, many things. So this is called the ceiling function, and it just means round up to nearest whole. That would probably be the easiest way to do something like that. Or you could do a piecewise, or you know. One more, I'm gonna do one more, because now I'm kind of jacked about this. Or equals, and I'll do a piecewise. If k is even, I'll just divide k by 2. If k is odd, I will add 1 and then divide by 2. Notice that that would take something like when k is 1, I add 1 to it, I get 2. Divide by 2, I get back out 1. So that's another way. Not needed, but it's always heartwarming to see things like this. Because it's in your blood to do things like this. Okay, so we're good. Was 127 a problem? Thought so. Yeah? Or not? Was I wrong? It wasn't. Oh, it should have been. That's
No, it is.
It is, okay.
Yeah.
How are we feeling about that? Does that make sense?
Can I ask about C?
Yes, you can.
Okay.
This is, I gotta come in here and jostle. There's lots of jostling required. Yes, ma'am.
Okay, so C is the one where it says, show for an arbitrary function that it's always true that G of the union of A, or the intersection of A and
Yeah.
B is a subset of G of A intersect, okay, for all sets.
Yes.
So I guess my question is like, I can generate a set with actual numbers, but I'm struggling to generate an arbitrary set.
Gotcha. Let's talk about it. Yay! This is I signed these because I wanted to talk about these things because they're really important for us. So let's see. What are our assumptions? Just that G is a function, right? So let's see. So G is a function from R to R. This means it has R as its domain. It's valid on all of R. And I want to show that G of A intersect B is a subset of U. This is what happens when you get your books off Etsy or eBay, I guess. Show that that is a subset of the intersection of the images of each set. So the way I would proceed with this, Kayla, is to use set inclusion arguments. So in other words, if I want to show a set X is a subset of a set Y, I will take something from the left side and show that it has to be an element of the right side as well. That's the basic way to work with sets, when you're showing inclusion or equality. If you're doing equality, you have to do this argument both directions.
Right.
Yeah, so it's like an if and only if. So here, what I'm going to do is, this is an image of A intersect B. So I would take a y, and I like to use y because I'm really taking part of the output here. Taking something from G of A intersect B and working my way back down. So right now, if I take y out of here, what does that mean? This means that there exists some x in A intersect B that produces this output such that y is equal to G of x. So now, and if I take this much further, I'll have got it.
Okay.
This means something that you can break down into a
Yeah.
more granular thing and then work your way back up to over here.
Okay, perfect.
Yeah.
Thank you.
You're welcome. Other questions? I didn't give an inverse image one, did I? Okay, no. Okay, cool. I'll leave it be. No more questions, no more jostling. You have to self-jostle. That doesn't sound good. Let's roll on. I wanted to warm up with a little soup. Sorry, I didn't mean that to be honey, but then I saw it coming and went with it anyway. Let's warm up with some soup practice. So let's assume that A is a subset of B, and those are both subsets of the reals, and that B is bounded above. We want to show that the soup of A and the soup of B have some relationship between them, possibly. What do you think the relationship would be? I want to put something in the middle there, some comparator.
What's the right equal to?
Yeah, sounds pretty reasonable, right? Hell, it almost looks like it up here. So let's think about that. I've got real line. Here's B, maybe something like this. And A is a subset that lives inside there, so maybe A is like this. A is here. Seems reasonable to hypothesize that the supremum of B is greater than or equal to the sup of A. Would you take a few minutes and think about how you would prove this? And the thing you want to fall back on is the definition of soup. Right? We only have one, well, we have lemma 138, don't go there. Don't go there.
Don't go there.
Go with the basic definition of least upper bound. And I'll just give you a few minutes and then we'll talk about it and see if you have any ideas on how to proceed. So, I'm gonna say, how do you know this? So let's see, let me see, so soup A is the least, okay. Let me go through, so least one. Wait, okay, you're just writing out the code, okay.
Yeah.
So, okay. Oh, okay, sorry, this is the outline for your, okay, got it.
Yeah, sorry.
I'm
No,
like,
I
no,
didn't,
it's
like,
me.
write it out.
Yeah, yeah, so it's the least stuff about it. Okay, got that. That's super.
We're the same reasoning. I forgot to
Yes.
put that in there.
So I think you have approved it, and here's why. It's okay, who cares, it's all good. Because, so you're, right here in these first two, you're stating the definition of soup.
Yeah.
Totally proper. But then you're coming down, you're saying, okay, so this is the soup of this is the soup of this, and because they are subsets of each other, those soups must have this relationship, which is actually what we're trying to prove.
That they have.
That they have,
It's a
that
subset
if,
of
that
each
this
other.
implies this. So you're
Okay.
kind of falling back on does that make sense?
Okay.
Do you see what I'm talking about?
Yes.
Yeah, yeah.
Okay. Okay.
A little slower, it's a little slower, but it's subtle, and that's why we're talking about it. How's it going? Got any ideas?
Yeah, just let me know.
Going through- Okay, cool, that's good, that's good, that's good. If you're already done with that one, here's a trickier one. No, I think you're done with it, but, so you have a subset of reals. Bounded real. A little bit trickier result.
I'm having a little trouble with the last.
Okay, so let's see, so here's okay, so this alpha is your upper bound of E. Yeah? Uh-huh, yes, yes. I would be careful about the phrase greatest element of. There may not be a greatest element. Think of an open subset of just 0 to 1 open. There is no greatest element there, so your ideas are totally proper, but the language is not quite precise enough. And then, again, so that the greatest, right? We don't, that soup might not even be part of the set, right?
Right.
So, yes, I would stick to phrases like bounded by, and that's. Yeah, no, okay, all right, cool. Check right back in. Got any ideas on this? Yeah. Still kind of like throwing it out. Awesome. Let's talk about this first one, friends. I'm sorry to take the time, because I know you probably you might like to keep working on this, but we're gonna get lots of practice. And this is our like warm up, where it also, I'm gonna show you how to kind of work with these things. So the way I would proceed with this, and I think it's similar to what Noah did, and he can let me know, is first off, by definition, the soup of B is an upper bound on the entire set B. So that's just literally from the definition of suprema. So by definition of suprema, i.e. it's an upper bound. Yeah, everybody cool with this? So, but then, A is, everything that's in A is also in B, because they're subsets. So that means this is also an upper bound for A. So, but, since A is a subset of B, we also have, I'm gonna use little a here, is less than or equal to the sup of B for all A and A. Because all of those are also in B. It's just a sub-collection of these things up here. This is true for all of them, so it's certainly true for a sub-collection inside there. Okay, so now check this out. Now at this point, I know that sup of B is an upper bound for A. Right? So, let's just write a little note over here. Thus, sup of B is an upper bound for the set A. Sup of A is an upper bound for the set A. Also, sup of A is an upper bound for A. So I've got two different upper bounds for A. I've got one that's directly related to A, it knows A, and I've got another upper bound. How does the supremum relate to other upper bounds?
It's the least upper bound.
It's the least, so it's less than or equal to. So by the definition, because this is the least upper bound, so since sup of A is the least upper bound, and this is actually like part 2 of that definition, least upper bound, I'm gonna abbreviate that UB, we know that sup of A has to be less than or equal to any other upper bound, particularly that one. Does that make sense? And it's tricky and it's subtle. And until you see a couple examples, you really don't quite know how to proceed. But notice I'm just using that primal definition a couple of times. And I forget what definition that was.
132.
132, cool. So definition 132 is your friend for arguing about sups. Noah, did you make any progress on that evil or beast?
I think so.
Yeah. Do you want to talk me through it?
Okay, well, so I think what you do is you set up the inequality that for any A in A, sup A is greater than or equal to it.
Yeah.
And you can add C to both sides to show that C is an upper bound. Or A plus C is an upper bound.
Yeah. Or A plus sup A. Yes.
Yeah.
Yes, sir.
And then.
So let me write out,
you
that's
have
beautiful.
some- yeah, I didn't confirm that.
Okay, let's write, but that's a great start. So let's check this out. So let's look at the problem at hand. We've got another one here. We've got a non-empty bounded above subset. Notice I'm assuming bounded above on both these because the supremum doesn't exist unless you're bounded above. It would go all the way to infinity. So we have to have a stopping point to say there's a least stopping point. So show that if C is some arbitrary real number, then the supremum of C plus A is equal to C plus the sup of A. Looks sensible. Let's talk about what this notation means here. So let's say, for example, that A was the set 0 to 1. So that's literally the open interval. That's not a point. We don't do 2D in here. So it's this set right here. Then the set 3 plus A just says add 3 to every element of the set. So it's literally a shift. This is just a shifting motion. So 3 plus A would look like this. It would start at 4 and go to 5. Oh wait, no, 3 and go to 4, sorry. Add 3 to everything. So 3 plus A would look like this, just literally a shift by C. So Noah gave us a great start on this. We know a couple of things, and I should have written this in here, but let's just hit it now. So since A is bounded above, should have addressed this, sup A exists. So we got that. We also know, by definition, of soup, again, coming back to that, supremum, it beats everybody in A. And this is what you were saying, right, Noah?
Mhm.
Yeah, cool. So then if I add C to each side, that preserves inequality. You can add anything to an inequality on both sides and you still maintain that. So thus, C plus A is less than or equal to C plus sup of A. And so this is an upper bound on the set C plus A. So let me write that out. So C plus sup A is an upper bound, UB, on C plus A. Let me put a little quantifier there for that. All right, that's like the first part of being a sup. You're an upper bound. So right now we know this is an upper bound. We need to show it's the least upper bound. So we assume there's another upper bound and show that it's greater than or equal to this thing. Again, the same game as before, same game always. So this is satisfies part 1 of definition 1.3.1.
1.3.2.
Thank you, ma'am.
Yeah.
Thank you. Now we gotta satisfy part 2. So now it remains to show that C plus sup A is the least upper bound. For C plus A. Towards this end, let's let a B, little b, be an upper bound for C plus A. I want to show that's greater than or equal to this thing right here. What does it mean for that to be happening? Thus, C plus little a is less than or equal to B for all A and big A. So here's the trick that now has to happen. And this is a wormy trick. This is like a hard thing. You could spend days not seeing this trick. I'm going to get everything back to in terms of A. I want to forget about this C for a minute. So I'm going to subtract C from both sides. This implies that A is less than or equal to B minus C for all A and A. That means B minus C is an upper bound on A. B minus C is an upper bound for big A. Make sure this makes sense. Let me stop for a second, sip some tea, catch up with me, writing wise, thought wise. Because we're almost done. That was really the trick. Let me know if there's any questions or clarifications on that argument. Like I said, wormy and counterintuitive. So I'm going to ask you, can you bring this home? And the tip would be, now we know that this is an upper bound for A. How does it relate to the least upper bound for A? How does this quantity relate to sup of A? What is the next move? Yes, sir.
It's greater than or equal to sup of A?
Yeah, because sup of A is the least upper bound, absolutely. So it's an upper bound for A, and by definition of sup, the sup of A has to be less than or equal to it. What should I do next? Look at where we want to go, look for the rhythm of where we're headed. Do we see that rhythm hiding here? Yeah, we do. No, what do I gotta do?
Add C to both sides.
Add C to both sides. Look, so now we put the C back. Isn't that creepy? And take it over and bring it back a little later after we do some arguing. So, which implies that C plus the sup of A is less than or equal to B. B was an arbitrary upper bound. This is less than or equal to it. And this is also an upper bound. So this is an upper bound on C plus A. It is the least upper bound because it's less than or equal to any other upper bound. Therefore, so that's part two. So this shows that C plus sup A satisfies part two of definition 132. And that means this must be the sup of the set. Therefore, I haven't done that symbol in a while, that felt good. Therefore, the supremum of C plus A is equal to this number right here. Whew. That is tricky. Like, right, you could have spent days just wandering in the wilderness if you didn't see this trick. And of course, I've done this like 1,000 times, so.
Is that trick used elsewhere?
Not in our book. But, so Kayla, so that's a good question. Like, do we need to know this trick? Will this trick be on the test? Maybe, I don't know, probably not. But mostly what I wanted to do this proof for was to just show this definition 132 kicking in all over the place. And just that basic idea of arguing sans the trick.
Sans trick.
Sans, yes.
It's a cool trick, but it's like sneaky.
It is sneaky, yeah, it's really sneaky. Any other questions on that, friends? Because I want to move into, I want to get up on a hill and look at some things, especially about the axiom of completeness. All right. Quick private zero karma quiz. What is the axiom of completeness? You can just take a minute. Do you know what it says? We will abbreviate that. I'll often do AOC. Impossible to not think of a really cool, someone decent in our government for once. Kayla?
For every set that is bounded above, there must exist a least greater or a least upper bound.
Cool, so, exactly, and let's be extra, I'm gonna add an extra bit of precision to that language. So every subset of R. This is super important. So it's got to, we got to specify this. That is bounded above has a least upper bound. That is the axiom of completeness. That's going to turn out to be equivalent to a number of other things that we're going to hit this semester. It's an axiom, right? It's a fundamental result. And it says something about the richness of the structure of the reals. And let's get in there and see why not everything has this property. So let's just take a quick look at some sets. So here's a set, a subset of the real. This is going to be an interval. Let's just take a look at the interval 0 to square root of 2. And think of that as a subset of the reals. Bounded above, what is its suit? What'd you say? What'd you say?
Oh, it's in the reals? Okay, so then it would be, yeah, I don't know.
Let's draw it out.
For a second, I thought we were in N.
Oh God, no, okay.
So,
What's the least upper bound?
root 2.
Root 2, right? Yeah, this is like root 2. If I said this, surely we would know that the root, it's the sup and the max. But when I take that out, the supremum is the square root of 2. So sup of the set in the reals equals square root of 2. Let's convince ourselves of this a little more thoroughly. Because I think right now it's kind of like, I mean, I'm moving my hand, right? Making pictures that may or may not be real, putting ideas in our mind that might be misleading. So, what's the other way to show something's a sup? We got definition 132, and who else? Which are their major sup result?
Lemma 138.
Lemma 138. You're gonna know that number eventually, so we're gonna use it a lot. So lemma 138. Let's go back to that. Says, let's see. So we've got A is a. Do they say a bounded subset or just bounded above?
So assume S is an element of the reals, is
Oh.
an upper bound for a set A that's a subset of the reals.
Okay.
Yeah.
Okay, so S is an upper bound for subset of the real. Cool, and that says that it must be bounded above, so awesome. And then
S is a supremum of A, if and only if for every choice of epsilon greater than 0, there exists an element A in A satisfying S minus epsilon is less than A.
yes. Let's draw the picture. Let's draw the picture of something like this. So here's 0, square root of 2, and the claim was that the square root of 2, that point that fills in the right edge, is the sup. So let's think about what this theorem says. If that is true, no matter how far I leap to the left, so if I move here, let's call that, so square root of 2 minus epsilon. No matter how tiny that leap to the left is, there's still something in that set between here, or just to the right of here. So think about that. Make sure you get this idea of what that is saying, that no matter how far to the left I move from this supposed sup, there's something in the set to its right. Think about what would happen if we had picked the wrong sup. Let's say Oh, let's just pretend we thought it was 2. Some of you claim, the supremum is 2. Done, because my hand stopped moving. No. I can move pretty damn far to the left and not have any elements of the set inside there. 2 isn't in the set. If 2 was in the set, then it would be the supremums. 2 is the thing I'm claiming is the soup. 2 equals soup. No, that's bullshit. Because I move a little bit to the left, I move a hell of a long way to the left. And there's nothing in that set in that little interval. So this was a bad choice. Over here, there's no room for error. As soon as I fall to the left, I've got stuff from the set on my right. What is special about square root of 2? Let's list some cool things about square root of 2. What kind of a number is it?
It's irrational.
It's an irrational, and that means what, Noah?
It can't be written as one integer over another integer.
Yeah, beautiful. It cannot, it's not commensurate, right? It's this thing that upset the Greeks because they wanted everything to be commensurate. Everything was a nice ratio. And then, Pythagoras comes along, brings up shows the square root of 2, and then this causes all sorts of problems. He didn't die for it, which is shocking. But it was upsetting, right? That there could be this quantity that wasn't expressible as a ratio. Do you know how the proof of that goes? Yeah? Cool. Let's do it real quick together. So let's assume, because we're going to need this as an example over and over again. And this is in lowest form. In other words, it's simplified, right? I've taken out all common factors. So it's not going to be 6 over 8. It would be 3 over 4. So I've got this, I'm going to assume that it can be written this way. And that A and B are, let's just say natural numbers. I think we'll be okay. Clearly 0 is not going to be it. And there's no negatives needed. So then I multiply both sides, and if you already know this proof, go ahead and try to crank it out ahead of me. But if I multiply through, get this, and I'm going to square both sides. So 2b squared equals a squared. That says 2 must be a divisor of a squared. So like the factorization of a squared is 2 times some integer. So 2 is a factor of a squared. Thus, 2 is a factor of a squared. Well, if 2 is a factor of a squared, a is a times a, right? It's just whole numbers. So if 2 divides a squared, it must divide a as well. That has to be the case. Because if it doesn't divide a, then it can't divide a squared. Because these are whole numbers. And this all comes down to that. So 2 is a factor of a squared, and must divide a then. So in other words, a is equal to 2 times some integer, 2k. So that means a squared must be 4k squared. So now let's come back up here to this original relationship. If a squared is 4k squared, I'll come around here. You put these two together, we've got 2b squared equals 4k squared. In other words, we've got b squared now is equal to 2k squared. So using that same argument again, 2 must divide b. Thus 2 must divide b. So thus 2 is a factor of b. What's the contradiction? Yeah, lowest term. Yeah, we assumed the fraction didn't have any common factors in the top and the bottom, and now all of a sudden a 2 could be factored out. So this contradicts. This contradicts, see exclamation point, the assumption that A over B is in simplest form. Thus, square root of 2 cannot be written as a fraction. This is the thing that caused all the problems to begin with. Not that that fraction was in simplest form. So thus, this must be a lie. Cool, now we've got, that's the only one we know. If you want another irrational for this class, you have to prove it. So right now, the only irrational we know is square root of 2. There's a lot of others, but if you want to use it to prove for an example, give me a demonstration. Okay, so square root of 2 is an irrational number, and also, so we know that, so this is irrational. And that means it must have an infinite decimal expansion that does not repeat. If that expansion repeats, you can write the number as a fraction, which is kind of a cool thing, kind of a fun thing to do. So it's irrational, and in fact, square root of 2 is 1.414. I don't want to cheat. I want to say 592. Okay, I'll cheat because I wrote it down somewhere. No, I don't know where. Oh, here it is. 1.41421. Wow, sad. 21 and 356237. On and on and on. Okay. Square root of 2 is something like that, right? That's the decimal expansion. How do I know there's a number in here? How do I know there's a number, Michael?
They just did like the decimal like approximation for it, one term at like one decimal point place at a time.
Exactly. Check this out. This gives me a sequence of points converging to the square root of 2 from the left-hand side. So inside here, we can think of this is gives us a sequence converging, and we haven't defined that yet, so I apologize. Converging, to the square root of 2. So that sequence is going to look like this: 1, 1.4, 1.41, 1.414. On down the chain, each one of these is getting closer and closer to that. So you tell me how big epsilon is, I can find one of these that falls in that tolerance. And then we could get more precise about it, but it'll just be mind-numbing and not helpful. Just, do you believe that? Does that make sense? That's the key thing. Is that no matter what epsilon is, let me write that out. So, regardless of epsilon, which is positive, we can find a member of the sequence that falls in the interval square root of 2 minus epsilon to square root of 2. Epsilon's a billionth, no problem. Just find the approximation here that's accurate up to the billionth decimal place, and then move a little bit further out, and we're good to go. Does this seem true?
as much as anything in this class can be true, does this seem true? Yes, Michael, sir.
Just a question about the theme in this class. So,
Oh, no.
well, it seems like in other classes we learn how to figure out stuff. Is the thing in this class going to always be showed that it exists, but we have like no way of figuring out what it is?
No, we will actually do constructions of things. So I literally could construct this. I just don't think anybody has the stomach for it right now.
Okay.
And that it wouldn't help in the, right? But I could build this. Yes, sir. Yes, ma'am.
I was scratching my head, sorry.
Oh, okay. So we will be doing proofs, like when we get to epsilon, delta kinds of things and convergence, we will literally build things. That's one of the things I like. I'm sorry, I didn't mean to scare you with all the way this class has been. We will build stuff. That's one of the reasons I became an analyst. Because algebra was just like, what is happening? I had no idea. There was nothing to grab onto. But analysis is just like building things. Right now, we're just doing concepts. So it seems very airy. But it will become solid, I swear to you. Okay, so let me make sure I got time here. What time do I have here, friends? Oh, minutes. Good. Okay, so everybody feels, I'm assuming so, no one's said otherwise, that the soup of this set is the square root of 2. Let's change the set. Now we're going to live like a Greek. We're going to live like an ancient Greek. And we're going to pretend like we don't know anything about irrationals. So, we're going to take this set and Greekify it, ancient Greekify it. And I'm going to take 0 to the square root of 2 and just pluck out all the rationals. So I'm intersecting that with Q. So now, there's no irrational numbers in here. So this is pure rationals. If I'm only allowed to think of rationals, what is the soup? Take a minute. So, if we only allow rationals, what is the soup of 0 root 2? Yes, clarifying question, yeah.
Because part of me says that it will still be root 2 even though it's irrational, because there will always be a fraction forever closer to that, but it's never going to reach that.
Yeah.
But I don't know if that's.
But we're not allowed root 2.
I know, that I'm confused.
That probably is a good feeling.
Okay, good.
That probably makes sense to have that feeling.
Is this what it felt like to be an ancient Greek? Just like frustrated?
This is exactly what it felt like. This nails it on the head.
Good.
Yeah. At least like 3 of them.
There you go.
Since we only have a few minutes, let's talk. Any hypotheses out there? Michael, yeah.
Doesn't exist.
Why?
Because the decimal approximations of root 2 are finite and non-repeating, so all of them are rationals, and you can get infinitely close to root 2 by one of those Archimedean axioms. So
We'll talk about one of those soon.
yeah. So yeah, that doesn't exist.
So, yeah.
Doesn't exist.
So, any other opinions? Michael's saying there is no supremum if this is the world we live in. I agree. There is no soup. So, if we restrict ourselves, and Kayla was like, right, it's challenging because you're like, well, it's got the square root of 2 is the closest I can get, but I can't use the square root of 2. So what could it be? Well, anything bigger than the square root of 2 obviously would be a failure. It was a big old space right there, right? And just thinking about level 138, move a little bit to the left. Here, move that far. There's nothing in the set, so that couldn't be the soup. So you might want to try to pick one of these guys. Just like, okay, well, let's truncate this and make it irrational. The problem being that no matter where I pick, so let me exaggerate. If this is 1.41421326537, right there, clearly, I can move a little bit to the right by just finding out the next decimal in this expansion, right? So I can always come to the right. We could write a formal proof of this, but I don't think we need to. Does it make sense that there is no soup here? It hurts to think about it. It's a little painful, right? So there is the soup. This does not exist. Even though that set is bounded, it does not exist in the rationals. And make sure you put that. Because as soon as we allow these things called irrationals, soups exist. So why is this important? This says that we have to have all the reals, that there's something special about filling in all the holes that Q leaves. It gives us a completeness, right? It completes the set. It gives it a richness and a depth and the ability for this to happen, to be able to find a soup when you want to have a soup. And the way these two interweave, so if we take Q and then we toss in the irrationals, we get the real. So that's an I right there for irrationals. We will soon be studying how do these two even sit together. We have to have these, but man, the way these two interweave is crazy and wild and profound and exciting. So, yeah, I think that's all I got for you today, friends. Thanks for getting up on a rainy Wednesday morning to come here. Think about madness. Wow, I guess I don't see you till Monday, so have a good week. And I've got office hours Friday. If you need to meet some other time, let me know. We'll work it out. If you want to talk about any of this. Have a good weekend. Yes, I will. And it just has to say Dropbox. Thank you so much. I will create that.
See you Monday.
See you Monday. Bye. Good to see you, Diana.